So given an affine variety X and an open subset U, we have defined this ring OX of U of regular functions. And now the next question we want to study is, how do we compute this ring in practice? Like, how do you actually get it? Because at the moment, it's one of those very abstract definitions. And we get started with some of the most basic open subsets inside an affine variety. And these are called the distinguished open subsets. And the idea is, well, an open subset is the complement of a closed subset. And a closed subset is the solution set of a finite list of polynomial equations. And the simplest such systems of equations are those where you have a single equation. So in other words, a single polynomial vanishing. And those complements of those solution sets are these distinguished open subsets. And so the formal definition, you say you have an X and affine variety and the polynomial function f on X. Then we say d of f is just X minus Vx of f. So in other words, is the element of X such that f of X is non-zero. And here's the picture. These are called the distinguished open subsets of X. And we're going to see in the next remark that they have some nice properties. First of all, if you take a finite intersection, for example, if you take the intersection of two of them, then you look at the locus of X such that both f of X are non-zero and g of X are non-zero. And then this condition here is equivalent to asking that the product f times g of X is non-zero because the product of two elements of the field K is zero if and only if one of them is zero. And so this thing is just this locus here, but now you see this is again a distinguished open subset is d of f times g. But this is just kind of one of the rules to remember. Intersections just corresponds to taking the products of these functions. What about unions? Well, there, the formula, I mean, there's no such nice formula in a certain sense, but we still can learn something, namely, the claim is any open subset U in X is a finite union of distinguished subsets. And for this, well, an open subset is, again, the complement of a closed subset, which is the solution set of this finitely many functions. And we can write this solution set as just the intersection of the zero loci of each of the individual functions. Now we have to remember our set theory calculus. If you have X minus a union of sets Vi, then this is just the same thing as the union of all the sets X minus V1 up to, and so on, up to X minus Vn. So just convince yourself that this is the correct way to do this. And then, well, here we have this finite union, and now you see each of these things is just one of these distinguished open sets. And so we managed to write any open subset as a finite union of these things. And in topology language, this is saying that this collection of open subsets, df, is a basis of the Zariski topology. Any open is a finite union of these basic open subsets. And just to have an example in mind, like let's take the open subset inside A2, where you removed the closed set, which is just given by the origin. And then this thing can be written as the union of dx, the locus where x is non-zero, and the union where the locus where y is non-zero. And then keeping this picture in mind, what is now the strategy to compute OX of U of this big thing? Well, first you compute what is OX on this finite open cover. So if we want to understand the function on A2 minus the origin, we first understand what are the functions here, what are the functions here, and then we want to use that a function from this u to k is regular if it is regular on both dx and dy. So the idea is we first understand the simpler pieces, and then we patch them together, essentially. And so the calculation of this OX of df, this will be in the next video. But I want to show here an important tool which we are going to use there. And this is the lemma on the generalized partition of unity. That's a fancy name. Let's see. The setting is, again, we have X and F1 variety. And now we look at one of those distinguished open sets, df, and assume that this thing itself is a union of further distinguished open sets. So dfa, where A is in some index set B. And then the claim is there exists some m in the natural numbers such that f to the power n, is a finite sum. So this here is given by a finite combination of these fa, which cover the df, where the coefficients Ra are just some polynomial functions on x. So we started with df, and then we could write on this, and then we could write an equality inside ax, which said this f to the power m is some combination of the fa which appear in this open cover. Okay, so this looks a bit abstract. It gets maybe slightly easier when you set f to be 1, because then df, the locus where 1 is non-zero, this is everything. So df is equal to x. And so in that case, you have x is, assume that x is a union of these basic open sets. You take some cover of your entire variety by these basic open sets. Then the claim is, well, there exists this m such that 1 to the power m, so in other words, just 1, is a union of these, or is a sum of these Ra times Fa. And taking in further special case, for example, if you just have two things in this cover, so if x is covered by df1 and df2, then it says, well, you can find some functions r1 and r2 such that 1 is given by r1 times f1 plus r2 times f2. Now about these functions here, you see that this function r1 times f1, this is supported on df1. So in other words, it vanishes outside of df1 because outside of df1, f1 is 0. And the second function vanishes outside of df2. And that's a concept which you might have seen in other parts of mathematics, like given a space and an open cover, it's often very useful that you can write the function 1 as a sum of functions which are each supported exactly on this open cover. And just like this is useful in functional analysis and so on, this generalized partition of unity will be very useful when we compute this OX of df. Okay. The only thing left here is to show this, and actually that is not super hard with the things that we have seen before. Namely, well, let's start here. So we had this assumption df is covered by the df of a. And what we do in the first step is just take the complement on both sides. You take the complement in x, where the complement of df is the vanishing locus of f. The complement of this union here, complement of a union becomes an intersection. So it becomes the intersection here of the complements of these things, so the vx of the fas. We have this equality here, but then an intersection of vanishing loci, that's one of the properties of these vanishing loci, is just the vanishing locus of the sum of all of these, the ideas generated by fa. So in other words, we just get the entire ideal generated by all of the fa at the same time. So this is our basic observation just from on the set level. And then we want to apply the Nullstellensatz. So we take the ideal of functions vanishing on these two things. I guess here I should, to be consistent, I should have ix on both sides. So here, just take this equality and apply ix on both sides. Nothing happened yet. And then the two observations that we want on the left-hand side, this ideal of functions vanishing on this locus here certainly contains f. F vanishes on the vanishing locus of f. That's fine. And on the other hand, and this is where we use the Nullstellensatz, the ideal of Vx here, this is given by the radical of this ideal. And that's where this power of m comes from, because by definition, f being in the radical of this ideal just means there exists an m such that f to the m is in the ideal. But this ideal is just by definition, the ideal generated by this, this set of FA is just the finite combinations of the FA with coefficients in the ambient ring, so with coefficients Ra in A of x. And that's exactly what we wanted to show, that f to the m has this representation. And so in the next video, we're going to see how do we use this result to compute the regular functions on Dm.